Thank you very much. Can I be heard? I can hear myself. Is it a bit too loud? Okay, good. So first of all, thank you very, very much for the opportunity to speak here. It's really an honor. It's a little bit humbling for me. I'd like to thank the organizers for inviting me. And secondly, I would like to thank the organizers for arranging the talks as they have done. I get to follow Thomas. And essentially, I'm going to skim the cream. So he's been churning away the milk and done all the hard work. And I'm going to speak about some applications of ideas and problems that came up in his talk. So we saw one application, and I'd like to give a few more. And maybe, time permitting, discuss some other related problems and an approach to some of these applications that is a bit more low-tech and for a short talk might be more amenable, as I might be able to describe more completely. So the essence of the talk is going to be questions about taut foliations and deformations thereof. And the key techniques we're going to use or ideas come from contact topology. So the order of the talk will go from back to front. I'll start with foliations and some old stuff that's known to lots of people in this room, but maybe not to the younger members of the audience. And then we'll slowly move to these questions about deformations of taut foliations. So just to start, the first slide will be the first blackboard, which has disappeared. So M3 will be, again, a closed, connected, oriented through manifold. And Xi, or Xi, or Xi, depending on your dialect, will be a smooth. So smooth is key. C2 might be enough in a lot of situations, but less than that might cause problems. So we'll just say smooth. Co-oriented plane field, so it's given as a kernel of a globally defined non-vanishing one-form alpha. So I will really begin from the beginning, so something that's very well known, but I draw a picture, so I spend a lot of time doing it. So integrability, of course, as we heard, is about the exterior differential of this defining one form vanishing on the plane field itself. So in terms of forms that can be expressed concisely as saying that alpha wedge to alpha is of course 0. That's the condition that through every point I can find a little piece of surface that's everywhere tangent to this two-plane distribution. And those little bits of surface piece together to give a foliation of my manifold. And one thing about the foliation is that locally it's a stack of sheets of paper, so it has a nice local model in nice coordinates. It's just given by dz equals 0. Good. So now for some prehistory. So it's really prehistory because it's from Wood in 1969. So these integrable plane fields are very abundant. So any plane field is in fact homotopic to an integrable one. So it's prehistory in the sense of it's even pre-Thurston. So Thurston submitted his thesis in 72. So this is came before that. Maybe people know this proof of Thurston. That's Wood proved it a bit earlier. And another way of saying this is that the inclusion of the space of integrable plane fields, I call it Fol-M, foliations, into the space of all plane fields, hits every path component. It's surjective on pi 0. Every representative of a path component has every path component, has an integrable guy living inside it. So if you state it that way, a natural question is, what about injectivity? Or what about other homotopic groups? So this is a question that's considered by esteemed members of this room, but I'll just say it like that. So the question is, if I have two plane fields that are integrable, are they connected through integrable plane fields? Is this map here injective on pi 0? So the first results about this was by Lacranche, maybe from her PhD thesis, saying that if the two integrable plane fields you start with are sufficiently close to a fairly nice foliation, a taut one, just give the picture of a taut foliation, so every leaf has a nice closed transversal. Think S1 cross a surface, foliated by surfaces, the S1 fibers are the transversals. So if you have two plane fields integrable close by to a given fixed taut foliation, then she showed that you can actually find an integrable path connecting those two integrable plane fields. Okay. Then Hélène, in her PhD thesis, proved a very general result, but I'll mention what Thomas said. I'll just write it up there. That, again, you can connect any two integrable plane fields, assuming that they are homotopic, and that their tangent foliations are taut. So you can do away with a lot less than taut with some, I think even for generic foliations, it's now true. So for a nice open dense subset, I think it's true. So the one comment is that although you start with things with a bunch of transversals, the first thing you do with this transversal is you punch in a Reb component. So the first thing you do, unfortunately, is destroy tautness. That's sort of the first thing you do. So I also thank the organizers for putting this nice picture on the web page. Thank you. It made my life easier. So you introduce Reb components. So in particular, although the first statement here of Lagrange seems kind of local, start with things that are nearby to a given thing, the path you take is definitely not staying within a little neighborhood because things become very non-taut. You get Reb components with, of course, separating torus leaves, which cannot have closed transversals. So tautness goes out the window. So so you have the natural question of whether you can replace a lens result, whether you can replace two things tangent to taut foliations are homotopic through integral plane fields, are they homotopic through taut guys? So that's the next question. And we heard in the previous talk, the answer is no. So Thomas found an example of a taut foliation, which interestingly enough, as a plane field, is homotopic to its opposite plane field, so the plane field with the opposite coorientation or orientation. And of course, if the one guy is taut, then the same thing with the opposite orientation is also taut. But there's no integrable deformation between the two. By a lens result, there is a path of integrable plane fields, but in between something has to go wrong. And these guys were Briscoe spheres, we saw that, so they are small, so it turns out on those sorts of manifolds, I guess tautness and Reblessness are equivalent. So in this deformation, you have to have a Reb component. That's in this example here. So that's great. And I just want to say that these things aren't isolated. There's many of them, and I want to describe another sort of class of examples. So the first theorem is that there are infinitely many such examples. And you have pairs of integral plane fields that are taut, they're tangent to taut foliations. They're homotopic as plane fields, but not through, so they're not homotopic through taut integrable plane fields. So there are infinitely many examples, and pair is not important. You could take 2, 3, 5, 16, 500 million, but I cannot, you could even take infinite. However, if you add something else, then this becomes more difficult. So this result up there indeed remains true if you allow yourself diffeomorphisms as well as deformations, and if you forget about the orientation. So this orientation there is not so important. However, if you have diffeomorphism, then it's, I don't know if you can get an example of a fixed manifolds where in a given path component of plane fields, you can have infinitely many different taut representatives that are distinguished as taut foliations. That would be interesting, and maybe I'll come back to it at the end as an open question. So now a different kind of flavor of example. So these examples are on, again, Seifert fiber spaces in a sense, so they're very special guys. They're on S1 bundles, the unit tangent bundle of a hyperbolic surface, sigma g, which of course you can identify with PSL2R modular lattice, a Fuchsian group acting on the hyperbolic plane. And that has lots of lovely horizontal foliations given by weak or stable or unstable foliations of geodesic flows and so on. You have lots of nice horizontal foliations that are everywhere complementary to the S1 fibers. But you also have guys that look very different, guys that have torus leaves. So they look very different, and how would you think about getting such a thing? So of course I have a S1 bundle over a surface. Well, if I take a nice simple curve downstairs and cut open, what's left is of course a trivial bundle. I can foliate that, even I can foliate that. So how do you then close things up? Well, you have this thing, and you have two, so you've foliated trivially, and they're heading towards so you have an annulus, I've removed annulus because S1, they're heading towards a torus, and of course you need to spiral in. Okay, you spiral in, and you get a nice, so the point is that so my hands should be at different slopes. So the slopes from the left and the slopes on the right will look different. So it won't be a simple case of being able to match them up. You'll have to slide in and wrap around yourself, which my arms cannot do. So you definitely have such foliations, and it's not hard to see that their tangent distributions are homotopic. However, and they're taut if you take a non-separating curve downstairs, so a non-separating torus, that's still taut. But there is no taut deformation between the two. And smooth, I want to stress smooth here. So what's the point is that for smooth or even C2 foliations, the way a foliation looks near a torus leaf is restricted by Coppell's lemma, right? You know that the holonomy cannot be so exotic. So nearby tori, the way the foliation cuts it, the way we like to think about it, is in a linear foliation. You can't have funky holonomy, you can't have closed orbits and exotic stuff. If you allow C0, of course, you can spiral in all sorts of funny stuff. You can say C0, maybe C1, but I'll say C0. And you could, of course, spiral in such a torus leaf, and life would be fine. But if you want to restrict yourself to smooth things, that's not possible. So these examples are sort of interesting because you can distinguish taut foliations in this deformation sense actually without contact topology. So this is more some rigidity about the way things look by torus leaves, and these sorts of foliations, of course, on the unit tangent bundle of hyperbolic surface are also very rigid. I'll go back to that in a second, very special. So moreover, every integral path you could maybe imagine you might need to introduce some torus leaves, but non-compressible ones, so incompressible torus leaves to get Rabless foliations, but even that's not possible. So, of course, you can introduce a Reb component by just turbulizing along a transversal. That's the only thing that can happen in this deformation. Sort of, there's something interesting happening here. So that's another set of examples, and there's another flavor examples that generalize these Brieskorn spheres, and you can get all sorts of numbers of different components in the space of taut foliations using these contact techniques. So I want to now go to a more special class of foliations and different sort of questions, but also ones which are amenable to these sorts of ideas using contact topology. So suspension foliations, everyone again knows, but I've drawn a picture, so I want to show it to you. So just consider a representation of your fundamental group of your favorite, say, compact manifold, closed, I assumed at the start. And my notation for the set of all these things is rep, the fundamental group, to, and this representation should go to diff plus S1, so orientation preserving smooth diffeomorphisms of the circle. And of course, you can suspend that to get interesting foliation. So just as a reminder, I can take the universal cover of my manifold, cross it with S1, that's nicely foliated. And then I take the action given by the diagonal action, where I act on the universal cover by deck transformations, and on S1 via rho. And then I descend to the quotient to get a nice foliation. And if you take the simplest example where X is, I guess, S1, and you have R there, and I've taken a fundamental domain, this is just taking a cylinder and twisting the ends together with a nice, interesting twist, which means that these simple leaves become interesting. So the question I want to ask sort of in this spirit is, or problem in general, what is the topology of this space for your favorite kind of group? I said M was a 3-manifold, so the possibilities for this group aren't that many. So X should be a surface. If it's a sphere, it's pretty boring. If it's a torus, it's far too hard, and I refer to Ln. And I'm going to talk about higher genus stuff. Okay? We already saw that I referred to the cotangent bundle of the hyperbolic surface. So that's the next result is about the topology of this space. So an initial observation, easy thing, is that, of course, this representation space is partitioned by the Euler class. So different Euler classes, of course, give you different components. They're very distinct things. So how to topologize this, by the way. So pick a generating set, look at the values of your representation on a finite generating set, and then you get a natural map from the representation space to a product of this nice topological group, say, endowed with the C infinity topology. So what happens then for a fixed Euler class? What can happen? And the result is that for a fixed Euler class, even then, you can distinguish different path components. In general, for a fixed Euler class, for the representation space of a genus G, a hyperbolic surface, any G would do, for certain E's, which I will describe more precisely in a second, for a fixed Euler class, you get, in general, you get a non-path connected space. So let me just mention that people in this room have very well understood what happens in the maximal case. So the Euler classes here is, of course, bounded by the Milnor-Wood inequality. In absolute value, they're less than 2g minus 2. In the maximal case, Matsumoto G's have shown that you get a representation that's conjugate to a Fuchsian 1. So they're simple, and then you see a connected space, path-connected space. So E is not 2g minus 2, but I'll give the examples and say what E is. So here I just take rho gamma, Gamma is a Fuchsian group. So that's just given by embedding as a discrete lattice in PSL2R, co-compact. And then I take the fiber-wise k-fold covering. So I wrap around this PSL2R Augsburg Möbius transformations on the circle, and I just wrap around k times and lift. There's some choices in the lift, but take any one. In fact, different lifts will give you different path components. That's true, but maybe not so interesting. And that's a nice element in there for E equals, we'll see in a second. And the other guy, for the other representation, I want to take another Fuchsian representation for a genus G prime surface of lower genus, which is concocted so that you have this equation. So the Euler characteristic of sigma G prime corresponds to the Euler class of this lifted representation. So 2g minus 2, when you wrap around k times, you divide the Euler class by k. So it's not anything, they're very special, but these are the guys. And these guys cannot be connected in the space of representations via a smooth path. So I want to then discuss a little bit about a proof of that. So before I get to that, just some pictures. So rho 0, they were k-fold coverings of Möbius transformations, so the dynamics, and because it's a Fuchsian representation, all non-trivial elements are hyperbolic, so that's on the right. You have PSL to R dynamics, and you have one attractive fixed point, one repelling, and not something much in between. And when you take k-fold coverings, you get periodic points, 2k of them, arranged like this. The way I've drawn it, they're really fixed points, but they could have some rotation in there too. So the dynamics of these things look very different. Of course, rho 1, I'm sorry, maybe it was a bit quick here. Let me go back. So I said to take a lower genus surface, but I didn't say what I meant here. So maybe it's obvious, but I should say it explicitly. So I have the lower genus surface and the higher genus surface. How do I get from one to the other? I crush down a bunch of handles, right? We do a collapse map. So maybe a picture explains that. So the collapse map is maybe, here is my sigma G and sigma G prime, I guess. Sorry, sigma G. And I have some bunch of other handles. There's a big sigma G, and then I just collapse this guy to a point, and what's left should be my sigma G prime. So that's what I mean by the collapse there. So indeed, this map has big kernel. So first map has big kernel, so the composition does. Sorry. So what I've said there is a bit of a lie. Rho 1 has kernel, so the dynamics could look like that, or they could just be completely trivial. Got ahead of myself. And so, but it's true that on the left you always have 2k periodic points, and they're alternating attractive repelling. On the right you either have nothing, or you have just 2 fixed points repelling, attracting. So when you suspend those guys, you see these sorts of pictures, which is what a contact topologist might want to see. And you see alternating attractive repelling closed orbits, and in between a bunch of flow lines connecting them. And it's a nice more smell picture. And if I had a rotation, this wouldn't just be 2 separate ones. This guy might go up like this. But the point is that when you intersect with the vertical circle, you see the same number of intersections with red guys and black guys. And there the number is k, and there the number is 1. And that's kind of the key to this. So let me just now review the definitions of contact structures. We saw it already, but just to draw a picture for you guys to hold on to. Integrability was about defining one forms satisfying the equation alpha wedge to alpha being identically 0, meaning that through every point you had a little piece of surface. On the other hand, if through every point you never have a piece of surface tangent to your distribution, then you're totally non-integrable, meaning that d alpha never vanishes on the plane field. In terms of forms, that's expressed like this. Call that a contact structure, and foliations had a nice local model, and contact structures do too. Locally, they all look the same. And it's given by this nice one form, dz, or dz, I should say, minus y dx being 0. And that's going to be invariant in the z direction, in the x direction, which I guess is pointing into the board. And then as I move in the y direction, my plane rotates sort of uniformly in one fixed direction. Whether it's the left or the right is sort of dictated by whether I have a greater than 0 there or a less than 0. So by the way, I guess I've identified forms with functions, which I can do by choosing an orientation form, which is fine because my manifold's oriented. So I just want to mention one example and draw a picture. So the canonical on our friend, the unit tangent bundle of a hyperbolic surface. It's the only example that I'll talk about, I guess. So if you take that guy that has a canonical contact structure, defined as follows. So a point in this manifold is more than a point, it's a vector. So I'll call it V. So this contact structure, so it's a distribution. So I need to describe to you at the point V a dimension 2, a plane. So how do I do that? Well, I look downstairs, then I have my vector. That spans a one-dimensional subspace, which downstairs in my surface is codimension 1, and I just pull back. So I have my projection, I pull it back. So you might think that's a bit strange, and that's very canonical. Usually, in contact topology, I should take, I guess, the cotangent bundle. We'll see what happens there, but in this simple case, you can just take the actual tangent bundle, unit tangent bundle, and you see a picture like this. So downstairs, I've taken a fixed point. Above it, I've drawn the fiber, so I've unraveled the circle. And each point of the fiber is a vector downstairs. Yeah? And so what I've done upstairs is I've taken little normal disks and I've lifted these vectors, and this vector should project to the original vector downstairs. And what you see is when you twist around downstairs, as you move up the fiber, you twist around. Twist around, and how often do you twist around? Maybe it's easy to see in this picture, you twist around once. And this is an important thing. So you twist around the fiber once, and moreover, the fiber itself is tangent to this plane field I've defined. So these are called Legendre knots, in fact. I guess it's a knot. And you see that the plane field twists around once relative to this sort of parallel framing coming from downstairs. So that's important in contact topology. That gives you a nice invariance. So when you have a knot tangent to your plane field, you look at the framing you get. Framing is not quite a number, but to get a number out of it, you need to fix a base framing. But fortunately, because we're projecting downstairs, you pull back a framing downstairs, upstairs, and you get a base framing. So you get a number out of this. You really get a framing, a number. And here the number, getting the signs right, is -1. So each fiber, you see all fibers look the same, and this sort of propeller thing winds around exactly once. Okay? That's important. So that's the one example I wanted to talk about. And we learned in the previous lecture that we can approximate foliations by contact structures, but not really in a if you're careful in a sort of parametric way, but not in a naive parametric way. If you take nice enough foliations, you can get away with approximating actual families in a fairly nice way. So let's see what I mean by nice. So we learned about the theorem of Eli-Ashburn-Thurston, the very general one, that says any foliation that's not S2 cross S1 with its product foliation is approximable by contact structures. If you put in some extra assumptions, so if the foliation is not only without torus leaves, but without any closed leaves, like the stable foliations of anosal flows and stuff like that, and is not one without holonomy, So ones without holonomy are basically defined by closed one forms, or at least up to C0 perturbation, they are defined by closed one forms, or they are approximable by actual fibrations, so actual compact foliations. So if you're not in that situation, then you can start with your initial foliation and get a very nice way of moving it to a contact structure. We saw this deformation, and that's exactly what you get. And it's very, very nice in the sense that it satisfies some nice linear equation. You take your defining form alpha for your foliation. So psi is an integrable plane field. Let's say. Then you take a line, you can find a beta, so that the line starting at alpha in the direction of beta has called it alpha t, so it's a line of, it's a one parameter family of one forms, has the property when you stick it in alpha wedge d alpha, so alpha t wedge d alpha t, the linear part at initial time is positive. So this theorem says, under these assumptions, you can find a very nice beta, so that this, you have just an alpha here and you find an actual line, so that alpha plus t beta instantaneously becomes a contact structure. And not only that, it's up to first order it instantaneously does. So by the way, but t equals 0, of course, because of integrability, the 0th order part is 0. So this is really the leading order term here. And you see, if you take the derivative equal to 0, you just work it out. You get alpha wedge d beta plus beta wedge d alpha being positive. So if I assume my foliation has no closed leaves at all and is not without holonomy, we'll see when that actually happens, then you can find a beta, so that you have a really nice way of getting to a contact structure. So why is it really nice? Well, greater than is an open thing. So if I have a way of perturbing alpha by a beta, then I have a way of perturbing alpha tau for tau in some parameter space where tau is close to, say, the original, where alpha tau is close to the original alpha, right? So the closeness here is of alpha, so I fix my beta, and of d alpha. So because of this equation here, if I perturb things a little bit, nothing changes in the C1 topology. So I need derivatives to be controlled as well. The other great thing is that this condition is, of course, when I fix alpha, it's convex in beta. If I have different betas and I take a convex combination, fixing alpha, positivity is preserved. So that's exactly what you would want to do if you were naive and you don't want to work so much, is what I said. So if I started with my path of foliations or the tangent distributions, what I'm saying is if you have no closed leaves and no holonomy along the whole way, you can actually bit for bit, so a bit like this and then a bit more, and using, say, a partition of unity, you can perturb the whole thing to a path of contact structures, say, or you can have a Bldg parameter space, it doesn't matter. So the unfortunate, of course, this is very restrictive, but in the following application, which was to these representation spaces, it's actually enough. So let's get to the proof of this theorem B. So row 1, row 2. What was row 1? That was a k-fold covering of a Fuchsian group. Row 0, I'm sorry. Row 1 was then a Fuchsian group composed with a collapsing map, collapsing down a bunch of handles. And I assume that I have a one parameter family connecting the two. Well, what I do with the one parameter family, I suspend them and get a one parameter family, so F tau, where tau is, say, in 0, 1. Suspend to get a family of foliations, all transverse to the S1 fibers of a fixed bundle. Okay. Then I want to say I want to perturb this entire family like this. So I need to think why I can apply the previous Augsburg-Thurston linear perturbation trickery. Closed leaves. I can't have closed leaves because the Euler class is assumed non-zero. It's 2g minus 2 over k. Closed leaf is a section up to a finite cover. That means that the Euler class will be trivial. That's not the case, so no closed leaves. And without holonomy would mean I could approximate it by a fibration. Then I see closed surfaces again, and these can't occur for the same reason. So I can do this. it's fine. And then we learned when you have a one-parameter family of contact structures, that gives you an isotopy by Gray's theorem. And then I just want to say, well, the things you start with, so psi0 at the start and psi1 at the end are different. So good, done. Let me just give an indication why. So psi0 is actually, so rho was given by wrapping around the fiber k times, okay, and lifting a Fuchsian representation. Well, if you perturb a Fuchsian representation, that's sort of easy, because they come from the universal cover as nice left invariant forms. So sort of invariant forms on PSL2R, and you can just actually perturb very explicitly by doing a little computation. And it's not hard to see that if you deform, in the right way, you get a contact structure isotopy to the canonical one I described before. So each fiber is tangent to the contact structure, and you twist around once. And when I twist around k times, I twist around then k times. Okay? So each fiber is tangent to the contact structure and has this Legendrian framing is then minus k. Okay? Good. What about for the other gadget? Well, there I started out with something that was just Fuchsian basically, and I perturbed that. I deformed that to a contact structure, which I claimed. The claim is just the canonical one, and then I collapse down. So I pull back under this collapse map, and what was a contact structure becomes one of these things Thomas mentioned, a confoliation. So it might not be everywhere non-integrable, it might be integral in some places, but that's easy to fix. That's an easy sort of thing to do. So you take this confoliation and you can then easily move that to a contact structure, and you can do that preserving a large portion of the manifolds, a big compact piece. In particular, you saw this thing winding around once, you can actually leave that as it was. So, good. So what? Well, now Giroux tells us that you have a nice invariance of contact structures on such manifolds where you look at all possible representations of a fiber that are tangent to the contact structure, and you see what possible framings you can get. You take the maximal one. That's an invariant. So usually you can make these things more negative, but they're sort of restricted by some Thurston-Benniken type bounds to being not too positive. So this maximum is well defined. And the point is for this covering guy, Giroux showed that this invariant is minus k. And for this other guy, I explained to you just then that I found a representative where this framing is minus 1. So if you take a maximum and minus 1's in there, well, you certainly can't get minus k. And in fact, it's equal. So the invariant here is a kind of fairly simple, very clever one, given by looking at certain framings of the Legendrian knots inside the manifold. So that's the proof. We've just shown that in a fixed Euler class you have at least two, and you can say it's something like 1 plus k to the 2g components, path components. Okay, so the foliations I mentioned, of course, were very special. I've given it away a few times. They're coming from an ensemble of flows, so I'm not a great expert. There's many people who are much more experts than me with these things. Just to remind you, a flow is called an Nosov when you can decompose the tangent bundle as the flow direction, and complementary to that, you get a one-dimensional distribution, two one-dimensional distributions that span the complement, so that are invariant under the flow, and in one direction it's expanding, the stable direction, and expanding in the other. So I'll call something a Nosov if it's then, so then the plane field spanned by y, and the stable, the strong stable foliation, or the weak stable, I will call a Nosov. Get it standard. And by the way, this is a very nice picture. I want to dwell on this a bit. How do I perturb this foliation to a contact structure? Well, I leave the y fixed and I just tip that way. And my flow pulls this line that way and pushes it that way. So I see that this line, as I move this way, rotates in a fixed direction. If I tipped in the other way, I would rotate the opposite direction. Okay? That's a nice picture, and this is a picture that Yoshi Mitsumatsu has in his paper. These are very nice examples. So I mentioned it already, but let me repeat it. So Jus Matsumoto tells us that for a maximal representation, any other representation with that given with the maximal Euler class is, first of all, topologically conjugate to a fixed one, that's Matsumoto, and he showed that it's then smoothly conjugate, everything's smooth, to some Fuchsian representation, not a fixed one, you have moduli. But in particular, they're coming from anosov flows in the maximal strata. So my rho 0 was, again, covering of one of these foliations. So again, it's anosov, nothing changes. You lift an anosov flow, it remains anosov. And another way of saying what I said, which avoids reference to contact structures, but it's a bit of a shame, but that's how it is that any representation that's anosov stays anosov. So if you look at it now, a connected component, not just path connected, the connected component of an anosov representation contains only anosov guys. In particular, it's conjugate smoothly to a discrete subgroup in this k-fold covering of PSL2R. So in particular, my rho 1 was non-injective, so it cannot be in this connected component even. So not just path, when going a bit more to claim that it's not even connected this space. Okay, so what's the kind of mantra? We've kind of found a deformation invariant of taut foliations. This anosov property is sort of so stable and nice that it's really, so you know it's stable, so it's deformation invariant under small little perturbations, but somehow it's also globally stable. It's nice. So, a little summary. So what have we seen? It's convenient, or it's interesting to try and answer questions about deformations of taut foliations using contact structures. Well, what sort of foliations can you get, or what sort of foliations can you distinguish? i.e., let's turn the question around the other way. What contact structures occur as approximations of taut foliations, or perhaps even Rabelais foliations, or foliations at all? Those are the guys we can apply these sorts of ideas to. So for that, I need to first thank Patrick Masson for having this wonderful picture. So I need to remind you, so Thomas mentioned this word tight. Let me remind you what tight means. Tight is something that's not over-twisted. What is over-twisted? Over-twisted contact structure means that I have a disk like this, so that along the boundary, the contact structure is very tangent, so I have a degenerate locus along the boundary, and that's it. So, of course, the contact plane we see in this picture, another way of saying it is you have a disk, so that the induced foliation on the disk contains one elliptic singularity in the center, and then the boundary is again everywhere, is again degenerate. So it's everywhere tangent to the plane field. So it really looks like this picture. Okay, so that means over-twisted. Tight means not that, so there exists no such disk. Okay, I should say why this is amazing, and it is amazing because I mentioned in the beginning would result, and after you see this result, you ask the question I asked, I guess, or Ellen did, or other people. So over-twisted contact structures satisfy an H principle. So the inclusion of the space of over-twisted contact structures in the space of all distributions is a weak homotopy equivalence. So even on pi 0, that's very interesting. The surjectivity is much older. It's maybe due to Lutz and Martinet without the over-twisted bit. But the fact that if you have two contact structures, you can find a path between them, and therefore an isotopy, just when you have such a disk, is kind of really the amazing part of this. And that said to contact topologists that you don't want to talk about these, you want to talk about tight things. And let me just say one property of tight contact structures is that they satisfy Thurston-Benneken inequality. So their Euler class is somehow restricted, and it satisfies this sort of bound. For sigma, say, closed, kind of boundary, there's a sensible way of doing it then. But that thing maybe is familiar to foliators from looking at taut foliation. So you know, a taut foliation, its Euler class satisfies the same sort of thing. And in fact, I think even for Rabelais foliations, it's true. So without root components. So I guess the first great success of the approximation theorem was that if you have a taut foliation, and there's lots of interesting constructions of those, then C0 close to that, you always get a tight contact structure, and it's even better. it's tight even when you go upstairs to the universal cover. So universally tight here means that there's no such disk even when you go to the universal cover. So that's wonderful. You get all these non-over-twisted things just from Goodbye's work on constructing taut foliations. What about rabless? So actually, in their little book, they said the same is true for rabless foliation. So for a rabless foliation, you can find a small neighborhood in the place of in the space of plane field, so that every contact structure is again universally tight. Proof wasn't quite true, and Vincent Collard then subsequently showed that in such a neighborhood, you can always find some universally tight contact structure, but as we learned in the previous talk, not all contact structures in a neighborhood where you have rabless foliations and therefore potentially torus leaves are the same. They could be distinct. And actually, you can reinstate this original statement. So I think that's okay. So it is indeed true that the Augsburg theorem that they stated is the correct one. And this, I don't want to talk about any details, but the sort of things Thomas was talking about at the end about how sheets can look inside products of tori or surfaces plays an essential role. And if you go through that carefully, you can actually get back to this original statement that a rabless foliation always, so it has a neighborhood containing only universally tight contact structures. So that means the correspondence maybe between foliations, rabless, so you might think, looking at this, that taut and versus having reb components is the same as tight versus having an over-twisted disk, but rabless is the correct thing on the side of the dictionary. Rabless corresponds to tight. Having reb components corresponds to an over-twisted disk. So, good. So if I ask the question, what contact structures can approximate taut or rabless foliations, or even be deformations in this nicer sense that you have a one parameter family starting an integrable thing and instantaneously becoming contact and being isotopic to your given contact structure. You have restrictions on those contact structures given by the previous things. They have to be universally tight. Okay, that's just, but also, of course, you have Novikov who tells you that the topology of a manifold having a rabless foliation is restricted. Fundamental group is infinite. It's either S2 cross S1 or it's spherical. Topologically, even universal cover is R3. And what about if I don't ask, if I delete taut or rabless? Well, the result of John Ettmeyer using a much older argument of Atsuhiro Mori says that any contact structure is actually deformation of some foliation coming from an open book type foliation. So the final theorem I would like to project is that if you restrict the topology a little bit to the sorts of spaces we've been talking about the whole time to Seifert-Fibered spaces, then you can sort of answer this question almost completely or fairly satisfactorily. So if you take a Seifert-Fibered space, so a space with a fixed point free circle action, so you can have a finite set of exceptional fibers with some isotropy, then if you assume that the topology of the base is positive, then any universally tight contact structure, that was the obvious necessary condition, any such thing is a deformation of some rabless foliation. Okay? And indeed, if you assume a bit more about the contact structure, I explained this invariant in the context of the S1 bundles, taking the maximal possible Legendre framings you can get, call that the twisting number. If you assume that that is not positive, then you can actually say that the contact structure is a deformation of a taut foliation. You can remove rabless. I should mention in the genus 0 case, it's false, but it's false for silly reasons. So, well, perhaps silly reasons plus unknown reasons. So in the genus 0 case, you have examples of manifolds that emit universally tight contact structures, but no taut foliations at all, given by certain small Seifert-Fibered spaces. But these things do not admit tight contact structures in both orientations, which is the actual necessary condition. So I want to conclude with two questions, which is exactly about this. So I don't know, people in this room maybe can tell me. Does any irreducible 3 manifold, pi 2 being 0, and having no connect sum, with infinite fundamental group, emitting 2 sort of universally tight contact structures in both orientations, which is the necessary condition, doesn't necessarily admit a foliation. Even better would be that both things come as from a given foliation. Somehow they converge to a foliation. And another one is something I alluded to earlier. Are there manifolds which admit infinite numbers of taut foliations that are distinct up to deformation and diffeomorphism? So after all that, I thank you for your patience, and I would like to say, ご清聴ありがとうございました。And finally, お誕生日おめでとうございます。Thank you very much.